Hello and welcome back to I Can Science That, where we do honest investigations of everyday science. Today's everyday science topic is something we're all familiar with, and that is inertia. I'm sure we all know what that means, or at least we think we have a good intuitive grasp of it. But what I'd like to do today is take us a little deeper into what we know and understand about the origins of inertia, what causes that, and what do we know about that? Well, I'm going to start you with what I think we're all pretty familiar with, is that mass has inertia. Anything with mass has inertia. I think we understand that. And what is mass? Mass was told to me in high school, mass is just a measure of the amount of stuff that you have. If you have more mass, you have more weight. And if you have more mass, you have more resistance to acceleration. Newton's second law here, that we learned very, very early on in high school physics, describes the ratio between how much force we apply to an object and how much acceleration we get as a result. And this equation tells us that the more mass you have, the less acceleration you get out of a given force. So from this equation, we can describe what's happening here is there's some resistance to acceleration, and we call that inertia. If you apply a force to something, it will accelerate, but the amount of acceleration you get, it's resisted by how much mass you have. And so that's how this was described to me, and I think most of us think of things in these terms. But putting this together, we look at this equation, and we're going to run with this. What we're literally saying here is this m term is the amount of resistance to acceleration that you get. And that was literally the definition of the word inertia. So maybe, rather than saying mass is the amount of stuff in an object, which was sort of vague and unhelpful, maybe we could say that literally mass is inertia. Mass is the resistance to acceleration. More mass, more resistance to acceleration. Less mass, less resistance to acceleration. And that's what inertia literally is. What I'd like to do now is delve deeper into what actually causes this phenomena of inertia. Newton's law here describes how it comes about, how it works, how much we're going to get, but it doesn't really tell us why. Can we go deeper and ask why? A little background. Newton thought that inertia was an intrinsic property of mass. All mass has inertia in this ratio, to the point where you can just put mass into the F equals ma equation. That is what inertia is. But Mach had a different idea. Mach definitely thought that all motion must be relative to something, as we've discussed in our relativity investigations. So if all motion is relative, does that not include acceleration? If acceleration is relative, then this concept of inertia, which is resistance to acceleration, must also be in the same way relative. So that's what Mach thought. He thought that the external world is somehow forcing or pushing and creating that resistance. So to Newton, the resistance came from the mass itself. And to Mach, the resistance came from the outside world resisting the relative motion of the object. So what do we know now? Have we learned anything since then about how inertia works that maybe can ultimately answer this question? To dig a little deeper into the origins of inertia, let's do a little thought experiment. With the light box. So what is a light box? Let's imagine a perfectly sealed box like so, and the walls of this box are idealized mirrors. These are perfectly reflecting surfaces that will bounce the light 100% perfectly. Obviously, this is, just a thought experiment. So we'll imagine that such a thing could exist. So here I have a little packet of light, a little photon, and it's traveling along. It's going to go and bounce off of this mirror, and then it's going to bounce back and forth. So remember that that now that we've learned a little bit more since the days of Newton, we definitely understand that light, while it has no mass, light has momentum. And so each time the light bounces off the mirror, it's going to give that mirror a little bit of a push, little tiny push, right? So as that light bounces off the right-hand side, it's going to push the entire box, give it a velocity, transfer some momentum to that box. And the box now is traveling to the right. As the light bounces back over to here, it'll reflect again, and that momentum will be transferred back, and the box is now stopped. So then the process repeats, and over the course of bounce after bounce after bounce, we'll find that the box is moving at a constant average speed. So it's moving a little bit and then stopping, moving a little bit and then stopping, and that's in sync, of course, with the bouncing of our little photon. So that's what we find is if we just trap a particle of light in this perfect little box and let it go, the perfect little box will just be bumped along at a constant speed. Okay, what if the box is already at some speed? We put the box at some speed and then we put the light in it. What is that going to do? Well, remember, special relativity tells us now that any steady speed can be treated as if that is stationary. So that should make this entire problem very simple. Any steady speed at all for our light box will have the exact same results that we saw from the so-called stationary box. Any steady speed can be treated as if it was stationary. The box with the little particle of light in it can move at any speed we want, as long as it's a steady average speed. It'll get a little bump each time it gets hit by the photon, and then it'll get a bump in the opposite direction each time the photon hits the other side. And so it'll just be bumped, 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 bumped back and forth and maintain a nice steady speed at any speed that we're at. Rather than a single photon, let's go ahead and fill the box with many, many particles of light, many, many particles. And what we'll see is that instead of getting a single bump to the right and then a single bump to the left, we're going to get just a cascade of bumps, a series of bumps on both the right and the left. And as these photons bounce back and forth, of course, that's going to average out. So what we'll get now is a box full of light that has no resistance whatsoever to motion at any steady speed. Any constant velocity, the bouncing light pulses will create no net force on the box. The light will create an outward pressure trying to expand the box, perhaps, but since half the light is always pushing to the right and the other half is always pushing to the left, these should balance out, and the box should be happy with no resistance at any steady, constant velocity. Okay, so if we're all together on that, let's see what happens if we try to push the box. You give the box a little shove, like I'm going to come along here. I've got my little particles bouncing inside my box, and I just push. I apply a force on the box and push it to the right. So as the box starts moving to the right and the photons continue their little travel, you'll see that the photons that were headed to the left have bumped into the walls of the box. And I just, to make it simpler for the animation, and rather than having them reflect off, I'm showing them just keep on going. But these will have bumped. That one bumped, that one bumped, that one bumped. But these ones going to the right, they haven't hit yet. It's because the box is now moving with them, so that delays them from hitting, but it's moving against the left-bound light, and so it hits them early. We're going to feel this as a net pressure. There's more pressure now on the left side of the box than there is on the right side of the box, because we're hitting more photons on the left and less photons on the right. So the balance of photons bouncing back and forth is no longer balanced. We have a net pressure that we feel as a force pushing against us. If we push to the right, we feel a force pushing us to the left. Let's try it the other way. Let's push our box to the left. As we push our box, give it a little force here, push, we'll shove it over to the left. We see the opposite. Now we've hit some photons that were right bound, and we have hit fewer photons that were left bound. And this is going to create a net pressure pushing against the way we pushed. So, what did we just see? What did we just see? The box resists acceleration. The light inside the box will always push against us if we try to accelerate the box. If you move the box at a constant velocity, there's no problem. It'll just keep on going at a steady speed. But if you try to accelerate the box, you will get a resistance that fights directly against you, that pushes directly against you. And, let me add, the more light you have, the more resistance to acceleration you end up with. Now, hopefully, this is starting to sound kind of familiar in the context of inertia. What do we say we know about inertia? Is that constant velocity doesn't stop. We need a force to change your velocity. And when we apply a force, there's a resistance to the change in velocity, the change in momentum or the acceleration. There's a resistance there. And the amount of resistance is proportional to, we had said, the amount of mass. But in this thought experiment, we're seeing that the resistance is coming from the amount of light in the box. What we've just seen is that by putting light inside the box, we have created inertia. We just saw inertia emerge from a system that's just made of light and these perfect little mirrors. In fact, if we say that the box itself, all these mirrors, have no mass. Let's make them massless reflectors. So there's now no mass in this system at all. The reflection is still there, and the momentum of these photons is still there. So when you try to accelerate this massless box, you get inertia as a result. You get a resistance to your acceleration. And how much exactly is that resistance? Well, the more energy you put in the box, the more resistance to acceleration you get. And in fact, the amount of resistance with the units that we typically use comes out to be exactly E over c squared. And we may remember F equals ma. So where did we get this? Where did we get this from? Well, you may recall this famous equation, which is the rest mass equivalence in energy. If we have a body at rest of mass m, the amount of energy contained within that body is E equals mc squared. We usually hear that described as to mean that there's a matter energy conversion. Like you could convert matter into energy, and if you take matter and convert it into energy, this is how much energy you're going to get. We talk about that in like nuclear physics and stuff like that. What we're really saying with this is that this thing we call mass, which I have now argued means inertia, this thing that we call inertia comes from energy. Inertia is energy, and this is the relationship between those two. Let's talk now, instead of like a light box, let's talk about atoms, like the things that mass is made out of. So let's make our matter out of atoms. What are atoms? They're these little particles that are all bound together by nuclear forces and electrostatic forces. And one of the things we've learned through our chemistry class and our physics class is that virtually all the mass in an atom is in the nucleus, that the electrons have very, very tiny little masses, but the protons and the neutrons inside the nucleus, that's where the mass is. And well, then what are those protons and neutrons made of? And this is something that you've probably heard, but unless you've gone into like graduate physics, you probably haven't really dug into much. And that is, protons and neutrons are themselves made of particles. And those little particles, we call them quarks. So a bunch of quarks. The nucleus is just a whole bunch of quarks. And those quarks contain energy, quite a lot of energy. And that energy is being confined into the nucleus of the atom. So what we have here is an atom. An atom is nothing more than a whole bunch of energy confined into a very small place. And what happens if you confine energy? If you have energy and you can somehow stop it from running away at the speed of light by making it, bounce back and forth, or just hold it with a gluon field or something like that, what you get is inertia. And that is what inertia is. That is what mass means. If you want to know how massive your atom is, what you need to do is count up the energy of the quarks and bind them together. If you bind the quarks together into that nucleus, what you get is inertia. And we saw why by looking at the light box experiment. That's exactly what a nucleus is. And an atom itself, in fact. That the electron is bound, of course, to the atom also. And it's by holding it there on the atom, the result you get is inertia. All these little pieces of energy, they all want to fly off at the speed of light. Energy, normally, unconfined energy, travels at the speed of light. But if you can confine it into a little region so that it cannot escape at the speed of light, then that binding results in a region that resists acceleration as the momentum transfer becomes unbalanced through acceleration. Okay, and at this point, somebody wants to talk about the Higgs field and say, I thought mass came from the Higgs field. Yes, a very small amount. Remember the electron? I talked about the electron. The electrons have mass, but they're not made of particles that are bound together, as far as we know. Electrons get their mass from the Higgs field, which is a whole separate topic. Just understand that virtually all the mass comes from the binding of energy together into the atom, and a very small amount comes from the Higgs field. So let's summarize. What have we seen today? What have we seen here? Inertia is not, in fact, a fundamental property of matter. It is not a mysterious property of matter. We now understand exactly where inertia comes from, and we can call this an emergent property, meaning that the principle of inertia, the resistance to acceleration, is not itself foundational, but is in fact just the side effect of the fact that energy carries momentum. Energy carries momentum, and what we understand as matter is energy that has been confined into a small place. And because that energy can't escape, the side effect of that is literally inertia. Yeah. And here we have this equation coming up again, the equation we've all seen before, probably the most famous equation in all of physics, E equals mc squared. And that is not telling us that you can convert matter into energy. mean, that's one way of thinking of it, I suppose. But what it's really telling us is that matter is energy. Mass is a form of energy that has been, or many forms of energy perhaps, that are being confined by the forces of nature. The nuclear force, the strong and the weak nuclear forces bind these particles into the location of the nucleus, and that binding of energetic particles leads to inertia, which is what we think of as mass. Now that we have that background, we'll have a better understanding when we look back at the questions between Newton's ideas and Mach's ideas. We've seen that Newton's idea that it's an intrinsic property of matter, really not so much. It's emergent from the intrinsic property that energy has momentum. So that's the fundamental piece of information there that we need. And from Mach's idea then, Mach thinking that inertia emerges from the forces of external bodies acting on your test object. Does that have any validity? And hopefully we can look at that now in a future video and have a better understanding of how this all really works. Okay, I'll see you in the next one.